actually quite a simple one. It's talking about DC theory. So the DC circuits, the DC networks or the DC circuitry is a little bit more pushy than AC circuitry. The best way to describe it is that it is like a water pipe. So voltage is effectively your water pressure, and current would be your speed of water flow through the pipe. And with DC pressure going always in one direction during charge and the other direction during discharge, you do have to be cognizant of the path via your charge and discharge routes. So in my first slide here, I'm just covering the theory behind DC circuits and lithium batteries. I don't expect this to be completely comprehensive. So if anyone has questions over and above what I'm about to present, please speak up and I will include those questions later on. But a big component about lithium batteries is that their voltage window is a lot smaller than that of the lead acid window. So the operating voltage is basically only a 5-volt window, effectively between 50 and 55 volts. That's a lot smaller than lead acid, and so any errors in the DC circuitry or anything that causes the inefficiency in the circuitry will reflect sort of harsher on a lithium battery system. So number 2 point there, the DC cabling has that impact and the ability to influence the cell balancing and so forth with a lithium system. And point number 3 is that power loss is something that impacts your lithium power delivery, and it's obviously in relation to the current by the equation here, current equal to radius squared, and then I put in the term time, that's the T in there, to equate to kilowatt hours lost during the thing. So if you have a nice thick DC cable, aka 50 millimeter thick, you actually do get a better or a lower power loss and a better efficiency in a DC circuitry system. And what this actually means in relation to point number 4 is you want to remove as much resistance from the circuit as possible, so that all the resistance is basically represented by the losses in the battery, BMS, and inverter. So your monitoring losses become your best or your worst case touches. And you also want to balance the losses on either side of your battery system, so that the cabling from the inverter down to the battery and either side are balanced. Okay, that's point number 5. Path clarity is actually also very important. If you add in extra little pieces, or you bolt to different things, you need to make sure that you have a good understanding of what the path is. A lot of times you effectively set up a preferred path and you don't actually know about it. What seems a logical flow is not actually true. And then and the final thing on just in the theory is the battery represents a dam or a weir, which means that in the that water flow scenario, the water pipe scenario, you actually have a sudden expansion of that water pipe, which means the current on the other side of the pipe in a straight flow through is vastly reduced compared to the incoming pipe, or vice versa, depending on your charging and discharging scenario and the path. So you want to take that into cognizance when you're building your DC circuit. And with those little pointers, it's actually quite simple as to what is what the impact is in terms of your installation. So using those same points, all you do is you do a couple of things. Make sure that your cables are thick, 50 millimeters, or double up on 25 millimeter cable or 35 millimeter cable. You use the double bolt connections if you want to. By that I mean every terminal on the BMS and battery has 2 bolts, so they can carry a second cable, DC cable, and install large bus bars. I'll talk a lot about that, with a high cross-section integrity. By that I mean every time you put in a bus bar, don't drill in a whole lot of beginning holes or holes that you might fill. Rather leave that cross-section there across the entire length of the bar, and only drill a new hole for every bolt as you need it. Balance the load in the bus bar. So what I mean by that is that each bolt should be the same distance geometrically from the next bolt. And you should also try and do current symmetry. So you want to put the battery on one side, and then the solar charger on the other, and the inverter in the middle. So that way you ensure symmetry between the 3 systems that are, the solar charger, the inverter, and the battery. I have installers who actually will alternate that. So they go battery, inverter, MPPT, battery, inverter, MPPT, battery, across the same piece of copper bar. And that way they ensure that they have a decent spread and coverage in terms of no preferred path. Also, point number 5, the shortest DC cabling is always the best. And I'll be showing you a beautiful installation where they use massive bus bars in order to make sure that the DC cabling itself was as short as possible. Number 6, this is to prevent unintended preferred paths. Don't put multiple cables in the same lug or the same bolt. And then number 7 is a similar thing, for a similar reason. Don't bridge connections. Rather install a common bar and put cabling onto that common bar, aka the bus bar. And there's nothing against putting in 2 or 3 bus bars according to your requirements. Once you've done your installation, measure the resistance on this is point number 8, the resistance on the positive and negative parts. You can do that quite easily with standard equipment like a fluke, a multimeter, and match them up. A lot of times people do this measurement and they see that the resistance is so small that they can hardly measure it. But the fact of the matter is, if you just change the measurement threshold or the fluke's measurement, I don't know what you call it, bracket. From a ohm to a milliohm, you actually will get a much better read of the two cables and see how they match up. If you reduce the resistance as much as possible using DC cabling and balancing the paths, then the voltage and the current in either direction, the charge or the discharge states, the difference in those things become very small and dramatically less impactful. And since the BMS's balancing current is 0.2 amps per channel, per cell, your I've got two more coming in. Excellent. Let me just go there. No, okay. So your when you've reduced the resistance and improved the balancing of the two resistance cables, your impact on the BMS's ability to balance is much further reduced, and the batteries can operate as a 48 volt pair and be balanced and unimpacted in the balance scenario. And then the last point here is that every reverb battery set comes as a matched serial number. So either there will be a serial number with the letter A and the letter B on the end, or they actually carry the same serial number. And you must please ensure when you do the install that you use a matched pair. The reason for that is there's 8 cells in each of the sets. Actually, in the new C8, there's 16 cells in each battery. And if you use a matched pair with the serial numbers, the manufacturers have actually made sure that the cells in both batteries are matched in terms of longevity and in terms of the voltage. So when you put the two batteries in as a set, they will both have the same overall voltage and the same spread of internal voltages on each of the 8 cells. And that allows the BMS to start off at a very good state of balance. What we have done in our systems is we make sure that our cabling is actually doubled up. So you can see the cable guidance that we now give for a 12 or 24 or 48 volt system is everything above 35 millimeters. And if there is any question, rather double up on the 25 millimeter cable that we have provided in the past. That's the simple idea. I do also suggest that even though we're trying to keep the number of connections on each part as low as possible, that we put a fuse on both the positive and negative, and that allows the both parts to be balanced, and then a breaker upon every battery set. I have just got a picture here of one of my my batteries I'm just testing here in the lab. And you can see I've taken the reverb cable that we provide and doubled them up. So at the top, you'll see there's a big positive 50 mil cable coming in. It's attached to the 1 bolt. And then you have 2 25 millimeter cables swinging around as the black ones and connecting to the negative and positive. And then from the back end, you got the negative coming out, going up to the BMS, and that's also 2 cables. These cable lengths have been matched to each other. So all one of the reasons why we provide them is that all the cables are labeled here with these white tabs to give you an indication of how you can step them up. And they're also, their length, if you use them, will ensure you have negative and positive balance on both sides. What I did not realize is that people were not using these cables as their best guide, and then if their design was doing longer than 2.5 meters in terms of the total DC circuit run, in other words, from the negative of the inverter all the way through everything and then back into the positive of the inverter, that they weren't doubling up on it. They weren't making sure that this was at least a full system. So I'd like to recommend that people follow this picture or this guidance, because you end up then with a very low resistance DC system, and you really allow that BMS to balance across both of those batteries, and you don't favor one of those batteries. What I mean by favoring the battery, if the DC circuitry is a little bit out of balance, in other words, one of these, either negative or positive, is at a slightly lower resistance, you will end up drawing too much from one battery just on a discharge, as that dam effect or that wear effect comes into play. And then when you're doing the recharge of that battery, the opposite battery is then favored over the lower one. And everything I've just said up to this point is absolutely crystal clear, and I know everyone on this call is presumably rolling their eyes and saying, yeah, we know this is actually straightforward DC, or yes, Felix, I'm remembering my almost my high school DC circuitry, and yes, what you're saying is both true, and I remember it, but it seems too obvious, and I agree. However, and I'm going to beg pardon of any installer who recognizes their site. It's not intended. Here is a huge site. Okay, this is actually a 5-battery site with lots of solar chargers and 2 inverters. And you can see all the cabling for the solar panels coming all the way down here into here. And you can see all the thick 70 mil DC cabling coming through from the battery, which are just to the left out of picture. And this is a site that one of my favorite installers actually had to take over. And he left most of it like this. He did actually start adding in DC cabling because he was getting too much DC ripple on the inverter. And by adding the cable, he actually managed to reduce the resistance and the impact of the connections, and therefore removed his DC ripple. But he didn't get enough of a balance to improve the lithium battery handling of the disparity in all the cables. So you can see here, even on the BMS shunt, BMV shunt, sorry, he had actually ended up putting 2 cables on this lug, 1 cable in this lug, 3 cables in that lug, and another 3 cables in that lug. And in effect, he did not have any preferred path on there. So it all seemed logical that each one of those cables would be getting the same current and the same voltage. But in actual fact, especially if you have 3 lugs on 1 bolt, on the middle lug, you're starting to rely a little bit more on the fine edges and the screws to carry current as well as the flat plates. And the first lug is up against the copper bar of the shunt. That becomes a preferred path, and the last lug does not. And so even though it's all on the same thing, and even though it does not violate your DC theory, in other words, all of those things should be seeing the same voltage and the same current, you actually have set up preferred paths, and the least resistant path is the path that the current would dominate on. So another favorite installer came in and he cleaned up the site to look exactly like this. It's exactly the same site, but he just moved those inverters and the solar chargers into a different location and replaced all of those cablings with bus bars. So he actually has a service bus bar, which is these two bus bars here, encased in that's a copper bar all the way across, and they're encased inside the trunking. And then he has another double set of copper bars here for the batteries, and that's his storage bus bar. When he does that, you can see all of his DC cabling is suddenly reduced from 2 meters to, which was in the other picture, to less than a meter. So if you see in the picture next to you, he put every battery set, there's the 5 battery sets with the BMS in between, and these are the cables here to connect them to his breaker. Very important point, those breakers, he's got one breaker per battery set, and each of those breakers are 120 amp fused, and he has one on each part of his 50 mil cabling here. The result is that he actually has a massive, what I would like to call a voltage sink that that can actually, without any interaction from the BMS or from the inverters, can allow the batteries to balance in and amongst themselves. So as long as those BMSs are turned on, there will be a current bringing voltage and energy across the bus bar from battery to battery. And in that manner, each of these batteries, without even trying, they synchronize up to the same voltage. And that's one of the virtues of this, this idea of a bus bar. So what I actually see is quite common is on that fuse box that people use to protect the batteries, they might connect a little piece of DC cabling to the next one, to the next fuse pull box, and in that manner they deem that they've connected positive to positive, and they've created a virtual bus bar. It is in effect actually a point bus bar when you do that, and it doesn't create the same voltage sink idea. Now, I use the word sink here like a drainage sink quite deliberately, because that thick copper bus bar from the previous picture is doing exactly that. It's actually drawing all the voltage together so that they can always be at the same level, the same voltage. That I've outlined all in this slide, all the various gains from using a good solid bus bar. The point I should make is that if you have a one inverter, one battery system, you of course do not need a bus bar. The bolt connection between all the BMS to the fuse holder to the inverter is fine and good enough, and that does that is the lowest number of connections that you can make, and therefore is the desired design. But as soon as you have 2 or more batteries or MPPTs, solar chargers, or inverters, you must go with a bus bar. The bus bar is the biggest and most powerful way of finalizing or synchronizing your DC system. The 2 points I do want to highlight would be that the bus bar system is easily modified, and extra batteries can be added on very easily with just an additional cable. So it's one of the best ways of having a system you can actually even modify live. I've done that before, and it feels dangerous, but it's not at all. A voltage drop across the bus bars are much lower than the equivalent cable. And as a matter of fact, it's a great way of synchronizing your system. And then guidance in terms of balancing. So very quickly, you must ensure that every DC circuit that you install, that they're both balanced and as low resistance as possible. Number 2, make sure there's enough power going into the battery. These batteries are actually quite big tanks. They're quite large. So anything less than a 3 kilowatt production solar plant is not going to be enough. You need to have 3 kilowatts per battery set at least. And sometimes, as in the Cape, you probably need a little bit more, especially this time of year. When you have enough power, you will ensure that enough time is spent in both the absorption and float parts of the charge cycle. And then you also want to, if you get an hour of each, then you know that your BMS, your voltage bus on the inverter, and your BMV, if you have all of those, will all sync up, and they all will be correct. So even though if you don't have enough time in that absorption and float area, even though your BMV or your BMS reports 100% full, it may not actually be full. It's not synchronized to correctly. So the only way to do that is to make sure you do have enough power and you are in the absorption and float stage for at least an hour every day. Obviously, reduce disparate charge cycles. If you don't have your furnace, for example, set up correctly, you will have what they call frequency shifting to manage it, and you will have the battery being asked to charge, discharge the whole way through the afternoon. And the end result is when you actually are wanting to push out during the evening, you may actually be at a lower absorption, and you may have lost the synchronization between the BMS state of charge and the actual state of charge. It's not a big deal that the batteries will still deliver all of their power. It just won't report as nicely to the inverters and so forth. Ensure that your solar charger cannot bypass the inverter. That just means that you don't get a preferred path. So what I normally do is put the solar charger on the one end of the bus bar, the battery on the other end of the bus bar, and the inverter connection in the middle, and that way the inverter always sees every part of the current. And then always have the BMS in the battery system. I know this is seems straightforward, but people do forget that, or do not realize sometimes how important that BMS is. If you don't have that BMS on there, you obviously are out of warranty, but also your balancing goes haywire. If you want to, you can actually do a charge up current for a couple of cycles at a lower charge rate. The normal charge rate is basically 50 to 60 amps per set. You can do as much as 100 amps per set. Just make sure your DC circuit is correct and all your breakers are in place for protection in case you're doing 200 or 300 amps for several sets. But if you want to do just what we call a balancing charger, then you do a lower rate, 20 to 25 amps per set, and it gives you a little bit more time to balance. And then remember to obviously protect the battery with a 24 volt breaker. If I wait, sorry, I've just lost there. Okay, if I can quickly conclude by going to have a look at the BMS. This is the BMS I have in my my lab right here. You can see that all of these cells are well balanced at about 3.7 volts per 3.37 volts per cell, and that the voltage difference is 0.008. In the BMS actually won't even begin to start balancing unless that voltage difference is 40 points. So if I may show you there, the balance difference of 40 points is when it's highlighted in red, is when the BMS will start balancing, and it also only starts balancing when the cells get above 3.3 volts. So if I see about a 0.1 volt difference, I'm normally not alarmed. I know that the battery in the BMS will easily be able to handle it. It may be indicative that the DC circuitry is slightly awry, but most of the time it just means that you're at the peak. In other words, you're at about 100%, 101% capacity, and the voltages are all sitting above 3.4 on the on per cell. At that point, the number of volts that you have is number of cells that you have, and the amount of energy that you have per cell is quite a lot, and every additional pieces of energy can push the voltage up quite dramatically, because you're in the fast change area of the lithium voltage curves. If this call drops, which it's going to do in about 2.5 minutes from now, I will resume the call immediately afterwards, and so anyone who wants to carry on can do so. What I'll do when the call starts again is I'll actually move across to my BMS that's down here in the office and run through these screens live on my BMS. In the event that your system, this screenshot, for example, is showing you at about 94% state of charge and 206 amp hours going into it. This is charging. So I've got another 14 amp hours still to charge up. And you can see, even though I'm quite close to the top, I still have quite a good spread of the voltage differences. All these cells are very, very close together. And I mean, that's 1/1000th of a volt difference, which is really, really good for all 16 cells. And that's because I'm dealing with a matched pair of batteries. And well, the BMS has been cleaned up, and it's got a huge bus bar and so forth. So, in the software that we have for the BMS, I do have the ability to change some parameters. You can see here that I've got the protection and the alarm parameters. These I do not allow installers or other people in the third parties to change them, and therefore I do have a password protection for that. But I am allowed to adjust parameters to make it easier for the battery to look, a lithium battery to look a little bit more like a lead acid system. both because it's got
Felix, sorry,
16
I just want to confirm we're going
cells.
to restart the call now, right?
Yes, I am. I'm just wrapping up
Okay.
this one, just one last point. I've got 16 cells,
Okay.
and what I do is I have a, a, a pack over voltage allowance, which allows this thing to handle itself a little bit more like a lead acid system. Anyway, I'm going to just sign off here, and we'll resume the call immediately after this. Thank you, everybody.